Okay, I'm gonna do two things. So I'm gonna again, we'll be focusing on what we can expect to be tested for electrochemistry and then later for electrolysis. Now, for electrochemical cell, I already mentioned, first one, we need to always learn this E0 cell. E0 cell always have the formula, don't forget. It's always E0 cathode or anode, E0 reduction minus oxidation, E0 oxidation. Okay, I already said already, you can also write plus depending on what you have, but just follow the formula that you learned in school. Now, one thing we need to take note, whenever we do this E0 cell, is always learn how to come up with this half equations, alright? We always, in your data booklet, compare your reduction potential. So don't forget, the one that is always reduced is always going to be the more positive reduction potential. Okay? And then again, the one that is oxidized is always the less positive or the more negative reduction potential. We are always compare reduction potential here. Now, so this is one thing we need to take note of. One thing they like to test is please learn how to draw this cell diagram. Cell diagram is always not only referring to this SHE. SHE is your standard hydrogen electrode. If you were to look at your data booklet, we always learn that this H plus this E minus. Okay, this will always give me this H2. The E0 cell is always going to be 0 voltage. So every single reduction potential that you see in this data booklet is with respect to SHE. Understand? Okay. Now for this cell diagram, first thing is, I said already, please learn, that it doesn't necessarily mean that this one must always be the anode or this one always be the cathode. The basis is always based on this. Which one is more likely oxidized or reduced? So for example, if I were to have, let's say, this cell diagram, even if I want to measure the zinc, like you can see, right, the Zn2 plus to become Zn. The reduction potential, one thing we need to take note of, please know how to draw your cell diagram. To draw this SHE, hydrogen electrode potential, don't forget, always have to label hydrogen gas, always have to label the standard condition, 298 kelvins and 1 bar. For this SHE, because it's with respect to this H plus, anything with this ions that is in aqueous state, you have to make sure it's under standard condition where this concentration of ions is always maintained at 1 mole per dm cube. And because of that, there is no metals involved. The electrode will always be made up naturally of the inert platinum. Understand? So don't forget about this. Now, let's say, right, if I want you to determine, alright, this Zn. So Zn2 plus reduction potential. Equation is this. If you have anything that is already made up of a metal that you are trying to investigate what is the reduction potential of this half equation, the electrode that you want this to be made up of must always be the metal itself. Understand? So this one must always be the metal itself, okay? If this is actually not going to investigate the metal, then this one will naturally be this platinum inert electrode. Same thing, because you are making sure is under standard conditions, your Zn must also be 1 mole per dm cube. But is this all for a simple cell diagram? No. So again, you should also include this salt bridge here. Salt bridge, don't forget, always have two functions. The two functions of salt bridge is what, dear? First function? Maintain electrical neutrality. Number 2, complete the circuit. And number 3 is to what? Maintain electrical neutrality, complete the circuit, and we also try to, prevent the mixing of these two solutions, because they must always be maintained at 1 mole per dm cube. I said already, your salt bridge is usually made up of a more heavier ion like potassium and nitrate. They will not partake in the reaction here. So what do I mean by maintaining electrical neutrality? You notice how? Let's see, for this one, we know that the E0 cell reduction for your data booklet is going to be minus 0.76, right? So if this is minus 0.76 voltage, what do we learn here? Which one is more likely to be the anode? Which one is more likely to be the cathode for electrochemical cell? Which is more likely anode, the zinc or is it the platinum? The zinc is more likely to be the anode because anode we learn always undergo oxidation. Your cathode, which is going to be the platinum here, will undergo your reduction here. So at least I know that your this zinc will be actually your this half equation that is taking place. Zn will become Zn2 plus and 2e. If this undergo oxidation means the hydrogen must always undergo reduction, and this is what is taking place in your this half equation. Understand? So we know that electrons will flow from this direction to this direction here. However, is this always the case? No, it's not always the case. It doesn't mean that your this one must always be your this cathode. Alright? Doesn't mean SHE must always be the cathode. Sometimes it can be your this anode as well. I give you an example. Let's say we have your this iron. So this time I want to investigate my this iron. I'll be drawing another one. Okay, the reduction potential of iron to form iron 2 plus. Okay, so again, we always be drawing your SHE. The question is, same thing for this side. We know this one must be made up of platinum again. Hydrogen entering must be again 298 kelvins, 1 bar. And then here will be your this hydrogen ions, 1 mole per dm cube. Okay, same thing for here. This time, because is there any metal that you are trying to deposit or form in this dynamic equilibrium equation? No, right? And because of that, you should know this one must be made up of platinum. This is what I already mentioned. Any ions that is present, whether is it on left hand side, right hand side, any ions that are present, make sure they are always maintained. And you have to also write down here 1 mole per dm cube. Okay? Now, so let's try. For this particular case, based on your data booklet, what's your this E naught reduction first? So your E naught is minus, sorry, are you sure? So which one is most likely going to be the anode this time, which likely more likely to be the cathode? So that's why, do you see how this one is now the anode? Because this is 0.00. This is actually positive 0.77 voltage. So the more positive, always more likely to be reduced, right? So again, this is going to be my cathode. Cathode always undergo reduction, anode always undergo oxidation. So that's why we know the electrons are flowing in this direction. Okay, so this one, half equation that is taking place, since it's a cathode, it will be your 3 plus E gives me Fe 2 plus. This one on the other hand, the hydrogen is going to become your this hydrogen ions and then your electrons. Understand? So please know how to draw the cell diagram. They can still ask you to draw the cell diagram. You don't need to draw down your this equation, but you need to draw the setup. Clear? So this is the first thing they ask. When they ask you, give you this, right, please don't ever forget, because sometimes there is no hydrogen ions, okay? You still must write 298 kelvins, 1 bar here to showcase standard conditions, okay? Okay, because sometimes there is no gas. Clear? Okay, now, so this is first thing they like to test. That is related to your this E naught cell. Another thing is, I said that we always need to calculate spontaneity. Okay, so for your this spontaneity here, we already know this is always make sure your E naught cell is actually greater than 0, so you have your this spontaneous reaction. Obviously, again, same thing, if it's E naught cell that is less than 0, so it's more non-spontaneous. How about if it's equals to 0? What does that mean, dear? So this is at, equilibrium. Understand? So this is actually at equilibrium here. Alright? So please learn how to calculate your E naught cell, because later you'll see your E naught cell sometimes can also be involved in another formula. which is also what? Your Gibbs 3. Gibbs 3 minus NFE not cell, if this is also not. Now what does the not represent? Just tell yourself, the moment I write this symbol at the top here, it represents standard conditions, 298 kelvins, 1 bar. So sometimes if it's not a standard conditions, they will just remove this. Clear? Now, to do this calculation, just need to take note down. If you want to do some calculation like this, how do we usually calculate this E naught cell? We need to actually just make sure the two half equations that you are comparing, one of them must undergo reduction, the other one definitely must undergo oxidation, right? Agree? So I give you an example. So for example, if I put pieces of copper in bromine, okay? So I repeat idea is pieces of Cu metal is added to two things, to my this bromine and then to my this Ag. Okay, so let's see so whether they have any reaction or not. So again, this is usually saying that if they have any reaction with bromine, so what do we need to do whenever we want to compare whether a reaction will be spontaneous or not? Look at the data booklet, come up with the half equations. The first one is you have to choose if copper is taking place. The only reactions that copper metal can undergo is solely what? Oxidation. So you realize, do you see I have copper 1 plus and copper 2 plus that will be coming copper here? Which one do I actually choose? Do you think I choose the one with the copper 1 plus? Or do I choose the copper with the copper 2 plus ions to become Cu? Because both also involve in this Cu that undergoes oxidation. Which one do you choose and why? So usually 2 plus, why? More negative, because no matter what, you know this one, no matter what must go through oxidation, right? So you have to choose the equation where this copper is in its most oxidized state. So that's why we have here. What's the E naught cell here?
0.34.
So by the way, another way to draw this, you notice how I'm deliberately writing like this? So this is actually plus, please always tell me write plus or minus sign. This is plus 0.34. Notice the way I order, okay, is because I'm trying to showcase this is becoming this. Because if you write in the opposite direction, for example, E naught, Cu2 plus, and then this will become a minus already. So know the difference, okay, clear? Okay, now next one, we also have this bromine. Let's consider bromine. Bromine, right? Again, what is the half equation? Because copper, no matter what, must undergo oxidation. Your bromine, you have to choose. It must be the ones that undergo reduction. And we know there is only one equation down here. What's my E naught here, dear? So this is plus, sorry.
1.07.
So again, E naught, if I were to draw, this is Br2. Br, do you see how I don't need to write the stoichiometry moles? I also don't need to include my electrons here. This is plus 0.7, isn't it? 1.07. Okay, so now let's see. I'm provided with copper, I'm provided with bromine, so I know where copper and bromine is. If one undergo oxidation, we clearly see this one fulfills undergo reduction. There are some cases that both undergo oxidation is not possible. So is this possible? Yes. So if next step, then you do the checklist. E naught. E naught cell, we already know what is the reduction. So this is the one reduced, so we put that one first. It's plus 1.07. And then again, what is this? It's plus 0.34 because I know this is oxidized. Agree? So that's why what happens here, this one will therefore be positive still. That's why it is a spontaneous reaction. Understand? So same thing, if I were to have, let's say I change this up, sorry, Fe2 plus. So Fe2 plus, the next equation that I need to consider is copper undergoes this, right? So I will just write down here first, as usual. But if I have Fe2 plus, let's see, which equation do we consider? Because do you see, Fe2 plus, there is only how many equations that undergo this reduction? Sorry? One, which is the Fe2 plus becoming this. Agree? I cannot choose this equation at all. Reason being is because if you have actually your copper no matter what must undergo oxidation. If you choose this, you cannot have two oxidized reaction taking place. That's why I have to ignore this. Now if I have Fe, at least this one undergo reduction, it fulfills the first criteria. E naught for this is what, dear? Minus 0.44 voltage. This one is still plus 0.34 as we see above. And now we can calculate your E naught cell. So which one is actually reduced? This one here, minus 0.44, minus 0.34. So do you see how it's negative? It's not possible for copper to displace iron from its salt, since it's less reactive. Understand? Clear? So this is the next one they ask. This one is usually in combination with this electrolysis. Alright, but later we'll talk about that. So do you see this? The first thing, electrochemical cell will always like to test. Second thing the electrochemical cell will always like to test is your applications. Famous application, fuel cell. So I'm only going to go through the main ones. So famous application we like to go through. It's called fuel cell here. Okay. Now what I'm trying to say is that do we usually need to memorize? No need. But one thing on the famous fuel cell that you are expected in syllabus to know is this hydrogen oxygen fuel cell. Okay, so again, for this hydrogen oxygen fuel cell, you need to learn how to come up with equations when the electrolyte is both and let's say acidic electrolyte. So for example, this is the electrolyte here, which is acidic. I have this hydrogen and oxygen which will be supplied here. So my question is, if I tell you this is actually my anode, this is actually my cathode. By the way, anode and cathode, you should know this is going to be the negative terminal, right? Positive terminal, right? You know why this is the negative terminal? Because electrons always flow from the anode. So it's like a battery. Remember, electrochemical cell is like a battery, right? So negative terminal, positive terminal here. So can we see what we always supply at the anode? Yes, hydrogen. Don't forget, in your hydrogen fuel cell, this is one fuel cell we need to take note. No matter what, hydrogen is always supplied at the anode, oxygen is always supplied at the cathode. Understand? Okay? Now, the question will be, how do you write the half equation for what is happening at the anode and what is happening at the cathode? So, did I say need memorize? No need, right? Because in the exam, what they will always show you, they will show you what are the reactants and the products formed. Okay? Even for this oxygen here, let me just erase. Okay? Water is actually formed, hydrogen will recycle your hydrogen again. Alright? So, now let's try. Because we know this is at the anode, right? Anode hydrogen is always supplied at the anode, right? Agree? So what is happening to hydrogen here when it goes through this anode? We know hydrogen, what is it going to form? H plus, since it's in an ionic form. Okay? So all we need to do is just balance it out. That's why this one is the half equation taking place at the anode, right? Agree? And then at the cathode, so this is for acidic. And then at the cathode, what is the half equation taking place? We know O2 is becoming what? H2O. Can we balance as per normal, like redox? Yes, right? So we already learned oxygen balance using water, so that's why I plus 2. After which, balance hydrogen with H plus. After which, balance your charge with electrons, like what you did in normal redox. Agree? So, do you see that's why this is the half equation for anode and cathode? Now, however, what if I now change this up to become an alkaline, okay, electrolyte? Do you need to memorize? The products will still be the same, but do you need to memorize? No. Same thing. All you need to do is what? Do you see whenever you balance, what do we learn? Counteract any positive hydrogen with the same number of OH minus, right? On both sides, right? So H2O, okay, we know, sorry, H2, we know that because there are 2 hydrogen here, so let me just write first the side working, this is working only. Because there are 2 hydrogen ions, we know by your redox, balance both sides by the same number of OH minus. Then after that, what do you see? Do you see this one become H2O? So can I combine them? So this one becomes 2, H2O here. Next one, balance charge. Is the charge balance? So this is actually the balance equation. Don't need memorize, just use your logic. And then this one also the same thing, because there's 4 OH minus side working. Let me just write down the equation first. Okay, because of 4H plus, I write 4OH minus on both sides, since it's alkaline. After which, this one becomes 4H2O. Because there are 2 H2O, can I actually cancel out? Can. This one will become 2H2O if I bring over. Then after which, what do? Balance both sides, electrons. So this is the half equation. So what I'm trying to say is don't need to memorize. Okay, so fuel cell, this is fuel cell number 1. Hydrogen fuel cell is the basic one. However, I said before, because sometimes in exam they will never give you like strict hydrogen fuel cell. They can give you any other cell, right? It is your job to also know how to know what is the half equation that takes place. So this time this is hydrogen fuel cell. Let me change this up. So if I were to now change this up to a methanol fuel cell, so I will give you what are the reactants and products. So for example, we have here, which is my anode. I will say that I will have, again, methanol that is added. Carbon dioxide is actually produced. The other side, I have air that is added. And then I have water that is actually removed at the cathode. Inside here, this is actually a alkaline. Oh, sorry, acidic first. Okay, acidic methanol fuel cell. So I need to learn how to come up with your half equation, right? Now let's try again. Anode, cathode. So how am I going to come up with the equations? Very simple. What are my reactants? Methanol, right? Methanol, right? Yeah. Okay, methanol is what formula? Okay. And then, what will I form? Okay. How do I come up with half equation then? Like redox. Understand? So again, can you tell me balance oxygen or not? With what? So that's why here has 2 oxygen, here 1, so I have to balance with H2O. Next, balance hydrogen with what? So here got hot total of 6, right? So that's why here must have. Okay, then balance your. You see? Okay, next one. This is therefore balance. The next one, your cathode. What do we have? We have your oxygen becoming your H2O. So all I need to do is just balance this up as per normal. So do you see this is for acidic? What if I ask you to change this up? Now if I change up, I say this is an alkaline. So what will be the cathode and anode half equation? So this is acidic electrolyte. Now if I use the alkaline electrolyte, how will it be? Can you tell me? CH3OH plus both sides. Yes, I have to write 6OH minus on both sides. CO2, 6H plus, 6OH minus becomes 6H2O. Don't care about electrons first. But do you see how here H2O can I bring over? So if I bring over, it becomes gone, right? So the half equation is just this one, 5H2O, 6 electrons. How about the other one? Plus 4. We'll do the charge first. Here also must plus the 4OH minus. But do you see how this one becomes 4H2O? bring over, cancel out. So I'll get 2H2 over here. So all I need to do is just balance the charge for electrons, like that. Yeah, so I'm saying fuel cell know how to do well. Alright, so this is the first thing. They always like a test for electrochemistry. Alright, sometimes they will test you whether spontaneous enough. Alright, please take note, for spontaneous enough, the checklist is number 1, always choose equation. One half equation must undergo oxidation with the reactants that you're provided with, and the other half must undergo oxidation. Then only then you calculate your E0 cell, whether positive or negative. Other than that, you can also see, they can also test on your fuel cell. Please, sometimes if they give you a very foreign fuel cell, it doesn't mean you cannot solve, can still solve. Okay? Now, also for your fuel cell, this one is already in your notes. Please know the advantages and disadvantages of hydrogen fuel cell. Okay, so it's already in your notes on this picture. Okay, now can we continue? So, sorry, I need to answer a call. In the meantime, can you try question 1 first? Maybe. Oh, okay. We cancel. Very good. Okay, another one they like test is your electrolysis. So let's see for electrolysis here. So electrochemical cell is one thing, electrolysis is another. So the criteria for electrolysis is that you also have anode and cathode. But this time your anode and cathode for your electrochemical cell, electrolytic cell, sorry. Okay, you are having non-spontaneous chemical reaction, so it has to be, again, electrical energy driving this non-spontaneous chemical reaction. We should know from the battery, this is always your negative terminal, positive terminal. And because of that, you are expected in syllabus to also recognize that that's why this is a positive terminal and negative, this is going to be my anode. So what do you realize? Anode, by the way, still undergo always oxidation. At the cathode, we still always undergo reduction. But the sign switches. But is electron still flowing from anode to cathode? Yes. Okay? So always flow from anode and cathode. The only thing, the sign switches. Alright? So how do I remember? For electrolytic cell, you remind yourself, cathode is trying to attract cations. To attract cations, which are positive charge, you have to be negative charge. Anode trying to attract anions, so that's why you must be positively charged. Understand? I gave you criteria before. There are, again, 3 factors that can affect discharge, right? First one is your electrode potential. Agree? Second one is concentration factor. But the question is, I mentioned this before, when will concentration be a factor here?
If the difference is more than 1.
If E naught potential, okay, that is both, that can undergo the same discharge or oxidation or reduction potential. If your E naught, okay, the difference, okay, is lesser or equals to 1. Okay, that means it's not too large. So usually the significance, this is just a guideline by the way. Okay, not large. So this is just a guideline, alright? But when they show you like the difference, right? Usually if it's too, okay, large a difference like 2.00, alright? That is a very significant difference in E naught potential. Then you know concentration will not affect, even though it's a higher concentration. Understand? Later we do example. And then last one is what? Nature of electrodes. So how do we take note your nature of electrodes? I said before, nature of electrodes is anything that is under your anode. So this one mainly affects anode. Because you're this metal, right, that is non-inert, can only undergo oxidation, can never undergo reduction. Okay? So I said the checklist or the format that you do as your site working is always something like this. What happens to the anode and then the cathode, and then same thing, always tell me what are the particles involved. Particles can also include water. Okay, we also have, like for example, I will also have my this half equation. I can have my products, okay, and then what happens to your electrolyte. So this is always the format. Let's do a quick one. So let's say, right, both of them is made up of your this copper 2 sulfate. Alright, so for your this copper 2 sulfate, your this anode is made up of copper. Alright, so let's try the nature of electrodes first. Both of them are copper 2 sulfate. This is also made up of copper. So how am I going to do my this side working? So the anode, keep in mind this is copper 2 aqueous. Copper 2 aqueous also. So again, particles present at the anode, we have Cu2 plus, SO4 2 minus, and we also have H2O. We have to include. What else must I also include? Cu metal this time. The moment you see that the electrode is not made up of my this platinum, you must include in your half equations of consideration. Next one at the cathode, we should know also the same. Cu2 plus, SO4 2 minus, H2O, and then Cu. However, must we do it, to be honest, right, must we actually write both of them? No need. Why? Because we know always the more positive undergoes reduction, the more negative undergoes oxidation. So if you consider your cathode, cathode, we know that copper, okay, can undergo reduction. Sulfate, right, you never see an equation in your data booklet that undergoes reduction. But you notice how, for your water, you have here, but can copper undergo reduction? No. That's why you notice how I said that your nature of electrodes, that's why it only affects anode. Same thing, your anode always undergo your oxidation. Copper metal can never undergo oxidation. Water can, I can include. Here also can, I also can include. So far I'm left with this. Clear? Next one. What is the half equation taking place? This one is which one is preferentially discharged. Let's see. For your anode, let's see all the half equation in your data booklet. Do you see we have sulfate that undergoes oxidation? So what is the equation for the sulfate that undergoes oxidation? Yeah, so the E naught cell for that is what? For the sulfate, so I'll just write the E naught reduction. E naught reduction is S2O8 2 minus to become SO4 2 minus. This is plus 2.01. We also have water, right? So water is what? Which one that undergoes oxidation for water? We have to choose one that water undergoes oxidation. So it's what? So you know it's this one. So this one is actually plus 1.23, right? Last one is copper. Copper also can undergo your oxidation. So the E naught reduction that we consider is what? Now, so remember, we are always comparing E naught reduction potential. That's why I deliberately write as reduction potential. Usually anode undergoes oxidation. Which one is more preferentially oxidized? More positive or more negative? So that's why, do you see why half equation that is taking place is copper metal is going to be undergoing oxidation to form Cu and then 2E. Understand? Clear? And then take note, if we do the same for here, your water this time, half equation that we consider is that water has to undergo reduction. The only one that involves water undergoing reduction here, if I consider my E naught, H2O becomes hydrogen gas. This one is minus 0.83 voltage. Your copper again, if I consider Cu2 plus, Cu plus 0.34. For reduction, which one do we care about? The more positive one, right? Agree? That's why, do you see why? Again, this one will not get this discharge is actually your copper 2 plus, right? So the half equation is this. Okay? So products, you know that the cathode actually increase in mass, your anode decrease in mass since they are already made out of copper. This is just an example. Let's do one that is based on concentration. Okay? So concentration, this time I change this up. They are all platinum. So platinum, platinum. But I'll use again concentrated NaCl. Okay, aqueous state. So side working and just to refresh your memory, same thing. Anode, cathode, they are both Na, both of them NaCl. And this is the electrolysis of brine as well, but anyway. So for your NaCl, we have here, which is your anode. Again, do I care about Na? Definitely cannot undergo oxidation, right? So you realize we have Cl minus. What else? We also have minus H2O. Don't forget H2O if they are all in aqueous state. Here, this time, Na plus H2O. Usually I write concentrated at the top. So it reminds myself that I need to keep in mind whether I can consider this. Remember the consideration? So let's try. For your anode, can you tell me what is the E naught reduction potential for your chlorine?
Yes, 1.36.
So plus 1.36 voltage. And then how about the water again? Sorry? O2 gives you your this H2O plus 1.23. So same thing. However, let's see because there is something that is concentrated, right? Is the difference large? No, the difference is large. Not large at all, right? So concentration, can it be a factor? Can, right? Agree? So can your this, even though this one has a less positive E naught or more negative E naught, this one will be preferentially discharged. So this is the half equation taking place. This is why I always write at the top. Next one. Na, can you give me what is the reduction potential?
-2.71.
And then we know the water is already minus 0.83. So same thing, let's consider NA's here. Is the difference large? Very large. So significantly large. Can concentration be a factor? No. So that's why we know the H2O is going to just become your this hydrogen. Understand? So what's the products? Yellowish green gas evolve, but chlorine is also slightly soluble, later you'll see. And then what else? We also have hydrogen gas. But there's a third product, right? You know what's the third product? Because Na is always left behind, and do you see I form OH minus? I also form NaOH, which is your final electrolyte. Agree? So take note. Now, so that's why please learn your electrolysis. Learn how to compartmentalize your thoughts. So electrolysis, I said this is always a half working, but one thing we need to take note of is the applications of electrolysis. So applications, please note, is we always need to know the electrolysis of brine, which that's why I want to use concentrated NaCl. In your notes, I show you electrolysis of brine is actually unique. Reason being is because for your this brine here, alright, I said that with chlorine is actually produced and there's presence of NaOH. There is potentially a new product that can also be formed. In the electrolysis of brine, which is actually concentrated NaCl, please take note that you potentially can form what other new product? No. NaOH can react with HCl. This is under your group 17 here. So you'll form what? Any idea? You'll form NaClO. You understand? So this is also another thing you can take note, because this is under your halogens chapter, your group 70. If there is NaOH, potentially you can form your this NaCl, NaClO. Okay? Now, how come we need to take note about this? Is because that's why, right, for the electrolysis of brine, they will always like to ask a simple question: why is there a membrane that separates the anode and cathode together apart? So the reason being why you need to separate is because the Cl2 that's produced, you don't want it to react with the NaOH that it will be formed at the cathode side. Because you want to form again your this chlorine. If you want to just obtain your chlorine, okay, and your hydrogen gas, you cannot mix them up. If not, this will actually occur. Okay? So for the anodizing of aluminium, I'm not going to go through. For your this purification of metal, I'm not going to go through. What I want to go through is just the electrolysis of brine. Now, next thing about your this electrolysis, besides knowing which one is preferentially discharged, they always got to do with your formulas. So the formulas we always deal with is Q equals to IT. Hopefully you know Q is always in terms of what? Coulombs. This is always in terms of amperes, which is your charge, and this is always in terms of seconds. Alright? We know that your formulas always is this, followed by the number of moles of electrons that can be calculated as Q over 96500. These are the two famous formulas that we always deal with for this electrolysis. Something I need to point out is, whatever electrons that flow through the anode by right should always be received at your cathode. Okay, the total moles, that means if I have 5 moles that's moving or 2.5 moles moving, this one always receives 2.5 moles for reaction. Okay, the third reaction we need to take note is that particular formula. Do take note, this represents number of moles of electrons you have found in the overall equation between the anode and cathode. That means, for example, usually you want to balance these two up, right? So if you balance these two up, we know that electrons will be 2. So I sub this as 2. It's not number of moles of electrons of this, no. Your F will be your 96500, and then your E cell. Okay? It can also be E not cell. So your Gibbs tree, if it's negative, then spontaneous, positive, then non-spontaneous. Understand? So these are always the formulas that we deal with for electrochemical cell and electrolysis. Clear? But same thing, you should know. I'm just rationalizing the main things. Let's try every question right now for question 1, 2, 3 from this worksheet. I'll be writing on the board the answers, and then I'll walk to you to mark. question one? Time up. Which is the position of equilibrium you're talking about? Can you tell me, is it? Now you must tell me that actually is which particular one and it's not both. You see this one, at least you know that this one would cause this to shift, right? So you should just rewrite your equation there, because this is just one reaction taking place. This doesn't show an equilibrium. You know what I'm talking about? So you must write that this one, then reversible arrow, label this as maybe equation A. And then this one, label this as equation B. Then you can say position of equilibrium and shift. This is a irreversible arrow. So if not, how? So again, you must tell me, how not produce less? Oh, you have misunderstand. No, it's the carbon dioxide will remove these. So when carbon dioxide will remove this, the position of this will shift right. Then what happens to your E0 reduction becomes more positive. You understand? Even though it makes sense here. The other one also the same thing. So idea is not because lesser carbon dioxide. You're talking about this one here. Because the carbon dioxide will remove the H plus, right? Causing your concentration of this to decrease. So POE by the Chapter shift left. You understand? So this is again, misunderstand now. Okay, so silent. Increase the concentration, become more positive. Yeah, so it becomes more positive. When it becomes more positive, your E cell amount of CO2 reactor will increase. Why will amount of CO2 reactor increase? You didn't explain to me. Because the idea, you have to think about the Q equals to IT, and then number of moles of electrons equals to that Q over 96500. Because that will tell you the amount of electron transferred per second will actually increase. And that's why your removal of CO2 increase. You understand? So again, no. Your explanation cannot accept. This one, how do you calculate? I asked you calculate, you haven't done it right. Calculate now, please. Yeah, please calculate. You're supposed to get plus 1.23 voltage. Okay, you get a plus 1.23. Okay, can you do the other one so I can mark? Anyway, I'll go through. Okay, since you already done this, let me just go through this. For the first one, right, you're gonna listen. So the first one, they say that your this E0, okay, is the reduction is plus 0.40, and then the other one is 0. So that's why reduction, okay, minus 0. So that's why you still can get positive 0.40. Now, but the other one, I need you all to take note now. Inside your this question that you have down there, they gave you in terms of your irreversible arrow. So you have to showcase your reversible arrow. You can label as equation 1 or 2 or A and B, whatever, I don't really care. So then after you explain, the idea is the CO2 for this equation is removing minus OH minus. So when you remove an OH minus, it will cause the concentration of your OH minus to actually decrease. So for your this equation 1, POE will shift where? Right. And when the POE shift right, the reduction potential for this will become more positive, because you are undergoing more reduction reaction here. So again, same thing at the anode, you know the CO3 2 minus will then remove my H plus. And then this will cause the concentration of H plus to actually decrease. So by the checklist, this one will shift left. This one here, reduction potential, because you're shifting left this time, will become more negative. So when it's more negative, you always must write down this equation for me. E cell is going to be more positive. Okay? Because minus minus become plus, right? So that's why we have the answer here. Okay, know the template. Next one, they say here, the higher the CO2, please take note, the more positive. Alright, you're this E cell. Idea is you don't just tell me, okay, because you have more concentration, that's why again, more rate of removal of carbon dioxide. No. You have to relate with current. Okay? So did the current increase, Vivian? Sorry? So one thing, take note, your this current, okay, increases like. When you are more positive, your current will increase like. Understand? And then because of that, you should know I, which represents as current, okay? So why will the current increase? Because most likely the amount of electron transferred actually per second actually increases. So if I have again amount of electron, because the amount of electron transferred per second increases, we know that the rate of carbon dioxide removal will actually be faster. Okay. Okay, I'm going to need to mark that one. The next one, please don't account now, it's just positive 1.23. What do you say? The cathode has high pH, anode has low pH. So you think about this. Under acidic conditions, right, will there be any OH at the cathode? OH minus at the cathode? To react and convert. No, right? There will not be any OH minus, okay, to react with the and convert the atmospheric carbon dioxide to carbonate, right? So the carbon dioxide air can be captured by the ED whatever S, EDSC, right? Cannot, right? Then now next one, at the anode. At the anode, right, there's alkaline, right? Then it means that will there be any H plus to react with the and convert the CO3 2 minus back to CO2. So it means that it will not be, cannot be removed, right, into a separate storage, right? That's the idea, lah. So that's the reason why, lah. Because this is the one that's supposed to react. If you have very low pH, you have no OH minus. So I want to see. Okay. I erase and write the answers for question 2 as well. Cathode is the one with the H plus there. I'm talking about anode first. Sorry, at the cathode. Sorry.
At the cathode got high pH, so then it's got more OH minus to it.
But under what conditions? The cathode has high. I see the question. So just why a typical hydrogen oxygen fuel cell cannot be used. Hydrogen oxygen you know what's hydrogen oxygen fuel cell?
Yeah.
And the cathode is always what you supply.
Hydrogen. Oxygen.
And then the anode. So question is, for your this a typical why cannot be used in your this CDS is because for your this cathode, for your this hydrogen fuel cell, is there any OH minus in acidic conditions? And then in alkaline also, because there's only strictly either acidic or alkaline, you understand what I mean? So in your acidic condition, there is no OH minus. Even if I change my electrolyte to be alkaline, then there is no OH plus. Does that make sense? You're not asking for this one, you understand? through it, Vivian? Because I went through with you. Let me check first. Graph. Sure. Fine. And set your answer. Okay, so I'll just go through one listen, one listen. So the proper way that we actually need to craft is that if we are comparing a hydrogen fuel cell. Hydrogen fuel cell, you have only either acidic or alkaline electrolyte. So if you consider an acidic condition, then you can see how there is absence, okay, of minus OH minus, okay, in my this electrolyte. So the absence of OH minus is no longer able to remove or convert this carbon dioxide into this carbonate. Okay, so next one, hopefully you know, under alkaline conditions, let's say if I change my hydrogen oxygen fuel cell to alkaline electrolyte, there is also absence of H plus ions, okay, at the anode. So that's why, again, cannot convert carbonate back into carbon dioxide to be removed into a separate storage, okay? What's the keyword you're looking out for 2A part 3, Vivian? Maintain one. Yes. Because you should know there's loss and gain of this cation ions and anions, therefore overall positive negative charge. This K plus, NO3 minus, they will actually move to the respective sides of a Haas cell in order to restore the electrical neutrality. Yeah? Answer is on the board, but I'll walk around and see you working, especially for the description part. So you have hydrogen peroxide and you have VO2. So the first one is that sometimes there may be more. Okay, so the VO2 class is here. And we also have another VO2 class here. So you can undergo both oxidation and reduction. So let's see hydrogen peroxide first. Hydrogen peroxide is acidified. Most likely it is this equation. Okay, so they insist that this is added to that is containing my VO2. So now let's try. They are saying that what could be a possible color change, right? So you want to consider this equation and you want to consider this where you get a positive E naught. But you have containing this then. How can both undergo, wait, oh you change it up. So this is what value? You mean the one that you want to choose that undergo reduction or oxidation? So you want to choose this that undergoes oxidation. So it's actually 0. Do you think that is the proper one to choose then? 1.77, you minus 1 is still 0.77, is possible one. So that's why this one can cause this to actually undergo this color. Because you want the most oxidized state. Remember? What's the oxidation state of V? Here. +3. This one? So again, so you have 3 right? Here. So here it will be actually a, wait, this is not +3 here. This is actually +5. Right? +5. This is also here, is it +5? Yes, but which one do we actually choose? Do you see this one needs fewer number of moles of hydrogen ions in order for the reaction to occur? So that's why you will produce this. I can choose, to be honest, right? I can actually choose both. Okay? So you know that your hydrogen, but the thing is that I rather choose, let's say, the one that will form the VO2 plus this one here. Okay? So again, this here will be 6 plus, yeah, so this one here is going to be what color? Because this is actually blue color, right? What color would this be? It's in your syllabus to know. Yes, under transition metals that I boxed it up before. Huh? Blue. Okay, so this one will turn from blue to yellow. That's all. Understand? So there are 2 equations that I have to consider. First one is this one, which is obviously not possible because this will undergo reduction. So I need this equation to undergo oxidation. Understand? Okay, so yellow. So you need to show me that. Please never present as this. Next time you just present as a reduction equation. But what's the overall then? Since you already written down, you have to next write the overall equation and then you tell me what would be the color change. So that's how the marking scheme is like. Okay, write down the overall equation. Change, you should know. Show me the E naught is positive and then you say color changes from what to what. Okay? Hey, wait, I haven't marked for your front part. Can I mark your front part first? The one with the maintain electrical neutrality is the key we're looking for. Very good. Verify electrodes, very good. We're here at O2, so it means that we never say carbon dissolve. Keyword is called corrode. Okay, so the word is called corrode, not dissolve. Alright? Okay. Change corrode, then later you can continue to write the moment you finish. Then you take note. So for question part 5, please do circle. Usually graphite and platinum are known as inert. Okay, but the graphite, the only time when graphite is not an inert electrode is if oxygen is produced as a product at the graphite electrode. So the idea is oxygen can react with this graphite to form carbon dioxide, causing the mass of graphite to decrease. You say that the graphite electrodes is oxidized or the graphite electrodes is corroded. That's why they need replacing. Okay, but anyway. So repeat hydrogen, how come we choose this equation? Because hydrogen peroxide is provided as a reactant, and they say an instance is in an acidic condition, so only can undergo reduction. So if I want to choose, I have to choose, okay, since I have VO2 plus, that's why I have to choose this particular equation here, not this, since you cannot have two half equations undergoing both reduction. Okay? The way you're right, show me three things. Overall equation, E naught cell. So I'll calculate the E naught cell first. Reduction is this, plus 1.77, minus oxidation is that, plus 1.00. So you get plus 0.77 voltage, and you still have to write more than 0. Okay? Then you write down the overall equation, H2O2 plus minus VO2 plus, sorry, my bad, VO2 plus. Okay, so you will give me minus 2 VO, okay, 2 plus, and then you will say therefore observation. You are expected to learn what's the color. This here is actually blue in color. This here is actually yellow. This is under your transition metals I gave in my notes. Okay, you are expected to know. So solution will turn from blue to yellow. Or you can say blue to green to yellow. class on Thursday is at 3:30 to 6:30. You can?
Tomorrow.
No, when Thursday.
Ah.
Because I told you right, this week is slightly different.
This week, yeah, I can.
Can Okay.
3:30 to 6:30.
Because if not, then we shift out. Don't make them 6 o'clock, so you all can just after that go back. You need to give me 2 enoch cells. Because there are 2 possible further reactions that we need to consider, right? So if I have tin, this time add an excess of the VO2 plus. So VO2 plus, there's 1 here, and then we also have VO2 plus here. Okay? We learned tin, haven't finished yet. So first step by step. Tin, right? Again, can only undergo oxidation, so we have to choose this one that undergo reduction. We ignore this. Right? Agree? So we need to consider the first enoch cell for this. So the enoch cell for the first one, where you have again reduction, okay, plus 0.34 minus oxidation. So you get positive 0.48, which is actually have to write more than 0. So the first equation, we know that this 2 can undergo this reaction. We just balance it out. Sn, okay, must react with 2 VO 2 plus 4H plus gives me again Sn 2 plus 2 V3 plus H2O. We know by right, what's the color of this? And then this will become what color? Green. Please know. Okay, so at least we know the first reaction can take place because we clearly see how the enoch cell is actually more than 0. However, we have to consider whether further reaction can occur. Because do you see this one is also another one that you can undergo reduction if I have excess tin? That's why I have to show the other working. So again, I have to show another enoch cell. So enoch cell, again, consider reduction, okay, minus oxidation. So you get a minus 0.12 voltage, which is less than 0. Again, you have to show me that this will not occur. So, in other words, all you need to show me that reaction or solution or observations is that it will turn from blue to green. So you need to prove to me, because this is worth 1 mark, this is worth 2nd mark. You must have all 3, then I can give you all the marks. Okay? solution. Alright. Let me know if you cannot get the answer here. And when you're ready, I want you to do question 3. they already say we have 1 kg of this deposited. So you need to find the number of moles of chromium. Have you found? Let me double check whether your this chromium is correct first. Oh, 19.25, sure. Next one, number of moles of electrons. 3, right? Sorry, 1, right? So your number of moles of electrons is wait. Shouldn't you get your 19, then you can find out. By the way, you need to balance your equation.
But it costs is not negative. Why is it reduction? Because I'm using the wrong equation.
Opposite there. Means when this is reduction.
Isn't it?
So the thing is that, I know, so what they say is chromium is electrolytic deposited in an electrolysis. This is half cell. Okay, so now it's another kind of reaction. Clear? So in other words is you have to combine them together. You don't even combine. So you combine, then you already have this. Can you find the number of moles of oxygen? Can what? When you compare electrons, 19.231, you divide it by your 4, you this times your 3 lah. So 14.4 lah. Okay, so this is electrolysis. So once you get your this, you can find out your volume of oxygen. So I'll just write the working in the board. So for part B is another kind of question. It's not about your electrochemical cell. This is testing on electrolysis. So we know that if I have 1 kg of chromium, I can find the number of moles of chromium. Always have to present in terms of grams. Chromium is 52.0. So you should get about 19.1. So again, you always can present in 3SF, but you keep the actual in your calculator. You have to come up with your entire equation since chromium, okay, is undergoing reaction like this, and then the water will actually produce my oxygen. So all I need to do is just balance my equation, right? So this one you just need times 3, this one times 2. So that's why you get 2Cr. And then times 3. And then we have times 3. Okay? So that's why based on this mole, number of moles of O2 can be determined. Divided by 2 times 3 over 2, you should be able to get 14.4 moles. So volume, okay, is again 14.4 based on RTP. You should be able to get this EMQ, okay? Me just 1 minute now. Okay. Yes. I'm up. So voltage, please write units, monkey donkey. Feasible, able occur, yellow, can change color. Yes. Again, whenever they ever ask you why reaction takes a very long time, always tell me that you have very high activation energy. But another thing is that because this one involves sulfur dioxide undergoing reaction, right? And this is in the atmosphere, right? Agree? Do you think sulfur dioxide in concentration in atmosphere is going to be high? And some more you should learn in Set 4 is a pollutant, right? So I don't want to see the large intermolecular force attraction. You just need to take note, sulfur dioxide is either low in concentration. But one thing I want to ask, your this E naught star, right, they only indicate if the reaction is thermal, dynamically feasible. Or you can say how it is spontaneous or not. Okay, but it does not predict any rate of reaction. So the reaction is likely to have very high EA. I will accept as your other mark. You need to have both. And then another thing, you can say how there might be actually low concentration of sulfur dioxide in the atmosphere. Okay? The answer is actually behind. Okay, come, let's continue. This time we'll include both. Okay, this paper. We'll include a bit of organic chem. Do you see question 1, 2, and 3? I want you to do question 1, 2, and 3, also related to electrochemistry. I'll be writing answers on the board. You can use this as reference if you're fast enough. 1, 2, and 3, yeah? question 3 first after you're done with 1. But do you know, or just by looking, we also know it's going to be half. Because volume of, if the current is the same, volume of gas obtained should be half, right? Based on number of moles of transfer current. But I said you're working, so it's also half. Okay, new question 3. Are you done?
This one.
You know why? This right, both of them by right polar. But this one is higher. Yeah, so Just to let you know, for question 3, this one deviates more. The reason is because this has a larger molecular cloud size. So that's why it's more easily polarizable to form stronger ID-ID. So it should actually deviate more from ideal gas behavior. Okay? Anyway, you can see for this, very good that you can calculate. So I shan't go through. So next one for B part 2. Take note, if the current was the same, volume of gas obtained should actually be half. Okay, based on the number of moles of electron required, but the volume of gas is actually 4 times lesser, so the current used also must be halved. So you also can prove to me my calculation. So you want to listen, don't listen is fine. So I'll just show by calculation how we can prove for 1B part 2. So again, we know what's the volume of this oxygen gas. The way I should show the word, Side working, no need proof, but it's just to showcase. They ask for anode current use. Again, this is aqueous sodium sulfate, so at the anode you think about your sulfate ions as well as your H2O. Again, the electrodes are all inert, so I ignore the electrodes. Same thing, Na plus and then H2O. If you look at this, this is actually more negative, so we know the half equation is your H2O becoming your O2, H plus, E minus. This one on the other hand, because the difference is very large, same thing, it will actually be H2O plus H plus. This you your this 2H2 OH minus. Okay? That's why we know the gas is actually, inside the anode is oxygen. The volume of oxygen, they say is 37.5 cm cubed. You find the number of moles of oxygen, 0.0375 divided by 24. Afterwards, you can actually find what is your number of moles of electrons. So it's going to be 0.0375. Number of moles of electrons, you realize this one is always based on this 4, so you times 2. Because, 4, because mole ratio is 1:4. So again, we get 625, 0.00625 moles. So use your this Q equals to your 0.00625 times 96500 formula. And that's why you get 603. So that's why your I equals to Q equals to IT, so it's 603. Time taken, the array says 10 minutes. Make sure you convert into seconds. So I get 1.005, 1.01 M3 So it's also half. So you either can do the explanation or you show the working. start with your overall first. Huh? Make sure the Gibbs tree that you will be obtaining based on this. Units for this is always going to be at first joules per moles. So you need to convert it back into kJ per mole. So your joules per moles, by right you're supposed to get 54040, right? Okay, so joules per moles, convert it to your this, you should get 54.0 because you always have to present in terms of kJ for Gibbs tree. You get this? Hopefully you know why 2 so it's based on the overall equation is 2. Okay? Okay, do question 2. You managed to get the answer, right? Got it? No? Tell us. Oh, you do the hydrogen but they already say it's zinc ma. Half cell. Oh, I know, but they already say it's zinc so no Okay, so for question 3, they already say showing the discharge and they show you what's the half equation on both sides, so it cannot be hydrogen there. Do you see? Is that N2 plus? They give you the 2 half equation one. Huh? And because both of them involve zinc, right? That's why do you see why I have zinc metal? Okay, as my electrode. So unless your half equation does not involve any metals, then you will use platinum. Okay, do question 2. tomorrow?
Wait, I realized I didn't do it, so I didn't do it.
Tomorrow lah, Thursday lor.
I'll still do it now.
Sorry?
Because I've done one before. Because it's the MRJC paper, it's not the RI one, so I thought I didn't do it yet. Oh, but
I'm talking about camp.
I also did it before.
Oh, you did before, huh? Okay. Okay, can. Even the bio, is it? Okay. I gave you another Hwa paper, so you can try. Answers is already attached in the group chat. Huh?
Is it a 2023 paper?
Hmm?
Is it 2023 paper?
Only in 18. gonna go through shortly. Just try to finish question 2 first. Are you at question 2C, at least? Okay. So what do you think subsequently your bromine can oxidize it to? Correct. So I just go through to C. So again, you should know, let's consider your bromine first. So if I were to have bromine is provided. Bromine can only undergo reduction. So I'm provided with, again, your thiosulfate, S2O3. So this is what I'm provided with. So thiosulfate can undergo this oxidation only. So let's calculate the first E0 cell. If you want to actually see whether bromine can react with thiosulfate. Reduction minus oxidation. So after that, you can see how you will get the value of positive 0.98. So you can see how this is actually feasible. But let's see whether once you form S4O6, so S4O6, you see is here, can also undergo further oxidation, right? So let's see whether the bromine can further oxidize this. Reduction minus oxidation. So you can see it's still positive. So that's why you get a 0.56 voltage when it's still positive. Same thing, the moment you form SO2, let's see SO2 can undergo further oxidation or not. So E0 cell, you have to show me all this to get the first mark. You understand? So again, this is 1 mark now. So again, you will say how this reduction minus oxidation. So you will get a positive 0.90. Okay, so what they say, next thing you just need to tell me, okay, therefore this bromine can oxidize S2O3 to S4O6 to SO2 and eventually SO42 minus. Okay? Next one, the iodine can or not? Can only oxidize to what? So again, if I want to show the iodine, I write another color. So again, since we have here, iodine is this time. So we calculate reduction minus oxidation. So we know that this is still positive, 0.545. So this is more than 0. So you can oxidize this to form here. So let's see whether you can undergo further oxidation or not. Same thing, E0 cell, reduction minus oxidation. So this one is positive, 0.03, still positive. The next one you need to showcase to me, E0 cell, reduction minus oxidation. So do you see I also can undergo? But the thing is that, question is, do you think even though this is actually positive, do you think the sulfur dioxide can be further oxidized to sulfate? Why? Even though this is positive, even though this is also positive, why cannot? Because if you observe this value, is this very large? And because this value is actually not very large, means that the extent for reaction is actually too small. So that's why you can say this iodine can oxidize, okay? This S2O3 2 minus to S4O6 2 minus, and then to this sulfur dioxide. Reason being, you say spontaneous, but extent of reaction is too small. So you have to see carefully, Okay, let's verbally go through question 2. For your reaction, because it's a bit of organic chem already, but it's related to this question. So we have butanone can be converted to compound C following the series of reactions. They ask you for the reactions and conditions for step 1. So step 1 is your ketone become A, right? Notice how you have N inside. So the only way you have N is what kind of reaction? Nucleophilic addition. So you say nucleophilic addition with what? What's the conditions? H with NaOH and you learn 10 to 20. If you learn cold, you also can accept cold. But you are right. You write KCN, I also accept. You write NaCN, I also accept. So it's HCN with trace, KCN, and then cold. Next one, your structures of A, B, and C. Again, I'm going to write the answers on the board. Structure A, first thing is, we already know, because it's addition, right? So addition, we have OH, CN here. This is your A. Understand? Next one, let's see B. Because B is undergoing what? Reduction, right? So this is actually reduced. CH2, NH2. You still have OH. C is you can have condensation, right? Agree? So again, condensation, and because we have the O, this N is going to, again, which is actually connected to, O. This is C. Okay? Because you know the acyl chloride, they can react with both this as well as the OH, undergoing condensation. So the final product is this. This will always lose H, this will always lose H. The other one will lose Cl, so it's actually HCl will be the byproduct if they ever ask. Okay? Next one, your this B part 1. What is the mechanism?
SN1.
So it's a SN2, not SN1. Do you know why? Must be SN2 because they already say, what's my rate equation? Huh? What are you talking second order? I'm talking about SN1 and SN2, nothing to do with first or second. So, question is, this is SN2 mechanism there. So it means that the NaOH, right, can direct, which is the nucleophile OH minus, is part of your rate equation, right? So part of your slow step, right, can means that it can immediately attack what? If it's SN1, your nucleophile are never part of your rate determining step. Okay, so SN2 mechanism is a one-step process. Answer sheet is actually behind, but let me explain why SN1 is not the mechanism here. If you have your this I, we have my this H, CH3, CH2, CH3. Your first step in your SN1 mechanism is this one will undergo heterolytic fission. This is part of your slow step. Do you see your slow step doesn't involve your nucleophile? But your rate equation, they gave you the nucleophile. Understand? So it's your one-step mechanism. So in my one-step mechanism, again, you can draw in 2D, I also accept. Idea is that you must show me the arrow, show me the delta minus, delta plus, how the OH minus nucleophile will actually attack here. Okay? So that's why, since I have my nucleophile and this is my slow step. You can draw your this half where you have your OH. This will be a minus H, CH3, and then eventually the answer sheet behind, you see how it will lose the I, so it can become the alcohol. Okay? Clear? The curly arrows in orange is a must-have with the lone pair of electrons. So they ask you to draw the energy profile diagram. It should be just one single activation energy, which you see from the answer sheet behind. Okay? Now, end of here today. I think the rest you can actually try. So we already tried countless of your this electrochemistry as well as electrolytic cell. So go back and revise. Okay? Alright, anyway, bye bye.